Look around you, right now, wherever you happen to be. The walls surrounding your room, the floor beneath your feet, the pavement you traveled across today, the bridges carrying cars and trains. Nearly every piece of modern civilization depends on one cold gray recipe: concrete. It is the second most consumed substance on Earth, surpassed only by water. To keep building the modern world, humanity produces more than 4 billion tons of cement every year. But that gray foundation comes with an enormous hidden cost. The cement industry alone is responsible for an estimated 8% to 10% of global greenhouse gas emissions, more than all the airplanes flying through the world's skies combined. And the scale of our dependence is difficult to comprehend. Between 2011 and 2013, in just a 2-year period, China consumed more cement than the entire United States used throughout the whole 20th century. Think about what that means. Every American highway, dam, skyscraper, bridge, suburb, and major construction project built from 1900 to 2000 required less cement than China poured in only 24 months. But now, this system is beginning to collide with physical limits. We are exhausting raw materials that once seemed virtually unlimited, while the enormous weight of our built environment continues placing pressure on natural ecosystems. For decades, conventional engineering treated this gray monopoly as permanent. Alternatives were often dismissed as unrealistic or impossible. But what if the future of construction isn't about placing even more weight on the earth? What if skyscrapers could be built without using a single drop of concrete? What if ordinary concrete could be mechanically squeezed until it became more than 80% stronger without adding expensive new ingredients? And what if barren, shifting desert dunes could be transformed into stable ground capable of supporting plant life in only a matter of months? Welcome back to Survival Roots. Today, we're exploring a remarkable collection of structural, mechanical, and biological breakthroughs emerging from China that are challenging some of the most basic assumptions about construction, material science, and survival. And beneath the massive industrial projects are principles that matter far beyond skyscrapers and highways. They reveal new ways of thinking about materials, waste, soil, energy, and resilience. Lessons that can also shape how we approach self-reliance. So let's go deep into the mechanics and biology behind these technologies and see what they can teach us about building smarter, lighter, and stronger. Part 1. The invisible sand crisis. Rivers drained, lakes stripped by the hunger for sand. Before we can understand why these breakthroughs appeared, we first have to understand the crisis that helped force them into existence. We are running out of sand. Yes, sand. That sounds almost ridiculous when deserts cover roughly 1/5 of the planet's land surface. If sand is everywhere, why not simply scoop it out of the desert and use it to make concrete? The problem is that desert sand is essentially useless for conventional construction. For thousands of years, desert sand grains have been blown across dunes by wind and weather. That constant movement slowly grinds and polishes them until the individual grains become extremely smooth and rounded. And that shape matters. When smooth, rounded grains are mixed into concrete, they do not interlock effectively. They slide past one another instead of gripping together, which makes them poorly suited for the strong aggregate structure required in conventional concrete. Construction needs a very different kind of sand. The sand traditionally used in concrete is rougher and more angular, shaped by water and geological processes, and commonly extracted from rivers, lakes, and coastal environments. Those irregular grains can lock together far more effectively inside a cement matrix. The problem is that humanity consumes this resource on an almost unimaginable scale. Every year, roughly 50 billion tons of sand and gravel are extracted around the world to satisfy our appetite for roads, buildings, bridges, dams, and cities. One of the clearest examples of what that demand can do appeared at Poyang Lake in China. At its peak, Poyang Lake became the location of what was considered the world's largest sand mining operation. An estimated 235 million cubic meters of sand were being removed from the lakebed every year. The consequences spread far beyond the excavation sites. Riverbanks collapsed. Bridges were threatened or washed away. Groundwater levels fell. Changes to the lakebed altered the movement of water so dramatically that the lake increasingly drained toward the Yangtze River like water escaping from an unplugged bathtub. The pressure became so severe that in 2001, the Chinese government introduced an emergency ban on sand mining along the Yangtze. But when a resource becomes extremely valuable, banning extraction doesn't always end the demand. Illegal sand mining expanded, not only in China, but across other parts of the world. Criminal operations moved into coastlines and river systems from India to Southeast Asia, while the price of natural construction sand climbed sharply. Suddenly, one of the most basic ingredients of modern construction had become a serious bottleneck. The industry faced a simple but uncomfortable reality: find a cheaper and more sustainable replacement for natural sand, or allow the continued expansion of the built world to become increasingly expensive and environmentally destructive. That pressure helped trigger one of China's biggest changes in construction materials. Part 2. China's manufactured sand revolution and rubble recycling. Faced with a severe shortage of natural construction sand, China began making a massive nationwide shift away from river sand. The replacement was manufactured sand, commonly known as M-sand. Instead of waiting for natural geological processes to create suitable grains, manufactured sand is produced mechanically. Freshly quarried rock, mine tailings, and certain types of industrial mineral waste are fed into heavy-duty crushing equipment. These machines break the material down again and again until the resulting particles reach approximately the same size range as natural construction sand. But their shape is completely different from desert sand. Because the grains have been fractured by crushers instead of polished smooth by wind, they emerge sharp, rough, jagged, and angular. Those irregular surfaces can interlock inside cement paste, almost like microscopic puzzle pieces, creating a tight structural connection between individual particles. And China adopted this material incredibly quickly. In 2010, natural sand still dominated the country's construction aggregate supply. But over the following decade, its use dropped dramatically. By 2020, natural sand represented only about 21% of the total supply. Manufactured sand eventually grew to account for nearly 90% of China's construction market. But the idea didn't stop with crushing fresh rock. By 2026, China was pushing the same principle deeper into a circular construction economy, by turning urban demolition waste back into usable aggregate. Instead of hauling demolished roads, brick structures, and concrete debris directly to landfills, the material can be sorted, crushed, processed, and returned to construction. Old structures become feedstock for new ones. Recent feasibility studies have even examined finely crushed recycled clay brick, known as RCB, as a complete replacement for natural sand in cement-stabilized macadam road bases. The results showed that this recycled material could reduce moisture-related shrinkage cracking. And from a survival or self-reliance perspective, the underlying idea is extremely powerful. Waste does not automatically have to remain waste. If you're building on your own land, the material already around you may have far more structural value than it appears to have. Local crushed stone or properly processed brick rubble can potentially become part of a new structural material, instead of being hauled away while fresh aggregate is trucked in from somewhere else. The broader lesson is simple. Before paying to bring new material onto your property, look carefully at what you already have. Sometimes what appears to be rubble is actually structural gold waiting to be processed. Part 3. Squeezing the weakness. Compression casting concrete. Now we come to the first major concrete breakthrough, a process that attacks weakness not by inventing a new chemical recipe, but by changing what happens physically while the concrete is still wet. To understand why it works, we first need to look at one of concrete's hidden structural weaknesses. Mix cement, sand, stone, and water together, and you create a thick, workable slurry. Normally, builders pour that mixture into a form and allow it to cure. Vibrating equipment may be used to remove some trapped air, but much of the process still depends on gravity and time. And here is the key problem. As ordinary concrete sits and hardens, water and trapped air can move through the mixture. When that water eventually disappears and air escapes, microscopic empty spaces remain behind. Those tiny pores may seem insignificant individually, but together they become a major structural weakness. There is another vulnerable region that matters even more. Around every piece of aggregate inside concrete exists a microscopic boundary between the stone and the surrounding cement paste. This region is known as the interfacial transition zone, or ITZ. In conventional concrete, the ITZ tends to be more porous, less dense, and weaker than either the aggregate or the surrounding hardened cement paste. And when concrete is placed under stress, microscopic cracking often begins in exactly these vulnerable regions. Researchers associated with Tongji University, the China Building Materials Academy, and Shanghai Jiao Tong University began asking a radically simple question. What if, instead of simply pouring the concrete and waiting, you physically compressed it while it was still wet? That idea led to a process known as compression casting concrete, or CCC. While the mixture is still fresh, plastic, and workable, it is placed inside heavy hydraulic equipment and subjected to pressures ranging from approximately 5 to 15 megapascals. 15 megapascals is an enormous amount of pressure, comparable to the crushing force found beneath roughly half a kilometer of water. Under that pressure, two important things begin happening inside the concrete. First, excess water and trapped air are physically forced out. Instead of relying on those materials to slowly move through the concrete during curing, compression removes part of them mechanically while the mixture is still workable. This effectively reduces the water-to-cement ratio after mixing. The original mixture can remain workable enough to place properly, but the final compressed material becomes significantly denser. Second, the pressure attacks the weak interfacial transition zone itself. The porous region surrounding each piece of aggregate is physically compressed. Voids inside the ITZ shrink by around 35%, while the total internal porosity of the concrete falls by roughly 45%. And the final result is dramatic. Compressive strength can increase by more than 80%. With far fewer internal pathways available, water, chloride ions, and road salts also have much less space through which to migrate. That means improved resistance to freeze-thaw cycles, chemical attack, and corrosion-related damage, potentially extending the working life of infrastructure by decades. And perhaps the most striking part is what engineers did not have to add. The strength gain was achieved using the same basic cement, aggregate, and water. No exotic new ingredients, no expensive proprietary chemical package, no completely new concrete recipe. The major change was mechanical. Instead of asking chemistry to solve every weakness, they used pressure to physically reorganize the material itself. Pure physics, applied at exactly the right moment. Part 4. The Symphony of Vibration. High-frequency vibration mixing compression casting can dramatically improve concrete when the material can be placed inside a press. But what happens when you're building something enormous? A highway, a subway tunnel, a marine dock, a structure far too large to squeeze inside hydraulic equipment. That problem leads us to the second mechanical breakthrough: high-frequency vibration mixing. Think about how ordinary concrete is mixed. Cement, aggregate, water, and other materials enter a mixer. Blades rotate through the mass, while gravity and shear forces combine everything together. From the outside, the mixture can appear completely uniform. But under a microscope, something very different is happening. Cement particles are extremely prone to clustering. As cement contacts water, electrostatic attraction and van der Waals forces can cause fine particles to stick together, producing what are known as binder agglomerates. The outside of these clumps becomes wet, while dry or poorly hydrated cement can remain trapped inside. In conventional mixing, an estimated 10% to 30% of cement clinker may never fully hydrate. That means some of the most expensive material in the concrete can end up behaving like poorly utilized filler. Chinese engineers attacked that problem by integrating high-frequency eccentric vibrators directly into continuous double horizontal shaft concrete mixers. Now the mixer performs two jobs at once. The shafts rotate and move the concrete on a large scale, while high-frequency vibration passes through the mixture simultaneously. Those vibrations can produce accelerations of 2Gs, 3Gs, and even 4Gs. At the microscopic level, the vibration behaves almost like millions of tiny hammer blows traveling through the mix, and it creates three major effects. First is deagglomeration. The vibration disrupts the water films and attractive forces holding clusters of cement particles together. As the clumps break apart, individual cement grains become much more thoroughly dispersed, and more of their surface area is exposed to water. Hydration becomes far more efficient, allowing the concrete to produce a dense network of calcium silicate hydrate, or CSH gel, the primary binding structure responsible for concrete strength. The second effect is nanodispersion. This becomes especially important in ultra-high-performance concrete, or UHPC. When engineers attempt to reinforce these advanced mixes with extremely small materials, such as carbon nanotubes or with millimeter-scale steel fibers, conventional mixing can create serious problems. The reinforcing material tends to cluster. Instead of being evenly distributed through the concrete, fibers and nanotubes can collect in localized groups, reducing their effectiveness. High-frequency vibration helps break apart those clusters and spread the reinforcement more uniformly throughout the matrix. XCT scans have shown the fiber distribution coefficient increasing from 0.512 to 0.581, indicating a significantly more uniform internal distribution. The third effect is pore refinement. As vibration moves through the mixture, aggregate particles themselves begin to resonate. In effect, every small piece of stone becomes another vibrating source inside the concrete. Large trapped air bubbles are driven upward and expelled, while remaining bubbles are broken into much smaller and more stable pores. At vibration levels around 4 Jans, total porosity has been shown to drop by as much as 28.9%, while water absorption can fall by more than 30%. Again, the breakthrough is not primarily about changing the ingredients. It is about changing the physical process. By improving how effectively existing materials mix and react, engineers can reduce cement clinker use by roughly 5%, while still achieving higher early-age strength, strong frost resistance, and improved watertight durability. The lesson is remarkably similar to compression casting. Sometimes, stronger material doesn't begin with adding more. Sometimes, it begins with using what is already there more intelligently. Part 5. Biotech in the Dunes. Soil seeds stabilizing desert sand in months. While mechanical engineers were squeezing and vibrating concrete, biological researchers in China were exploring an entirely different frontier. Their question sounded almost like science fiction. Could biotechnology turn loose, shifting desert sand into stable ground capable of supporting life, without pouring concrete over it or relying on conventional chemical stabilizers? Under natural conditions, stabilizing a mobile desert environment can take generations. Powerful winds constantly move exposed sand across the landscape. Dunes migrate, young plants are buried or ripped from the ground, and infrastructure can be slowly swallowed by the shifting terrain. Researchers at the Shapotu Desert Research and Experiment Station, operating under the Chinese Academy of Sciences, began looking toward a microscopic organism for an answer. Cyanobacteria. Cyanobacteria are ancient photosynthetic microorganisms capable of surviving intense ultraviolet radiation, severe dryness, and extremely harsh environments. Give them a small amount of moisture on desert sand, and they begin multiplying. As they grow, they release sticky sugar-based substances known as polysaccharides. Those compounds behave like biological glue. Fine sand grains begin sticking together instead of moving freely across the surface. Gradually, a thin living layer forms across the ground. This layer is known as a biological soil crust, or biocrust. But there was a major obstacle. Zhao Yang, deputy head of the Chapoteau station, observed that when researchers simply sprayed liquid cyanobacteria onto actively shifting dunes, the organisms disappeared in less than a week. The problem wasn't that the bacteria couldn't survive the desert itself. The problem was movement. Wind-driven grains of sand acted almost like microscopic sandpaper, repeatedly striking the developing bacterial layer and physically destroying the fragile biofilm before it had enough time to establish itself. So the researchers changed the delivery system. Instead of spraying cyanobacteria in liquid form, they developed solid soil seeds, durable pieces of solid cyanobacteria inoculum. The cyanobacteria solution was combined with organic matter and fine clay particles in carefully controlled proportions. Zhao Yang compared the process directly to mixing cement. The mixture was blended and then dried into tough, gravel-like pellets. Suddenly, the microorganisms had armor. These solid soil seeds could be transported, handled with machinery, and distributed over enormous desert areas, even from aircraft. Then the system could wait. When precipitation finally reached the desert, the pellets activated. The clay and organic matter helped retain moisture, while also providing an initial protective environment around the cyanobacteria, shielding them from ultraviolet exposure and the constant impact of moving sand. Within approximately 10 to 16 months, the bacteria could establish a highly stable biological crust across the surface, and the reported effects were remarkable. Wind erosion across treated areas fell by more than 95%. A stabilization process that could naturally require around a century was compressed to roughly 3 years. Organic carbon levels rose to more than 3 times those found in natural desert crusts, while nitrogen levels increased nearly 15-fold, helping create conditions in which grasses and shrubs could begin establishing themselves. And this technology moved beyond the laboratory. It became connected with China's enormous 3 North Shelter Belt program, with plans to rehabilitate as much as 100,000 mu, approximately 6,667 hectares, of desert within 5 years. From a survival perspective, the principle behind this experiment matters just as much as the scale. When soil begins eroding around infrastructure, the instinct may be to fight nature with heavier barriers, thicker retaining walls, and more concrete. But this project points toward another possibility. Sometimes the most sustainable way to protect land is not to overpower the biological system. It is to work with the microscopic living networks already capable of holding that system together. Part 6. The Steel Challenger, the B-Core Super Slab. We've seen engineers make concrete stronger. We've seen biologists turn loose desert sand into living ground. Now we reach a technology built around an even more radical idea. Instead of improving concrete, what if you replaced it? That brings us to B-Core, developed by the Broad Group in Changsha, China. Broad Group was founded in 1988. Then, in 2008, a devastating earthquake struck Sichuan. Tens of thousands of people died. Broad's founder and chairman, Zhang Yue, traveled through the destruction and saw reinforced concrete buildings collapsed across the landscape, leaving people trapped beneath enormous masses of rigid debris. That experience changed the direction of his work. He became determined to move away from conventional concrete and develop structures that could be lighter, more flexible, more durable, and far more resistant to catastrophic earthquakes. After more than a decade of development and an investment reported at around $1.25 billion, nearly 8 billion RMB, Broad introduced the B-Core stainless steel slab. At first glance, B-Core looks almost impossibly thin. The basic structure consists of 2 parallel sheets of stainless steel with a geometric array of hollow, extremely thin stainless steel tubes sandwiched between them. The concept takes inspiration directly from aerospace engineering, particularly the lightweight honeycomb panels used in aircraft structures. Honeycomb geometry allows engineers to produce tremendous stiffness while using relatively little material. But aerospace panels can be extraordinarily expensive. Broad's challenge was finding a way to manufacture a similar structural principle at industrial construction scale and at dramatically lower cost. Their solution depends on an unusual bonding process. Extremely thin copper foil is placed at the contact points between the internal tubes and the outer stainless steel sheets. The entire sandwich structure then passes through a continuous hot air furnace operating at approximately 2012 degrees Fahrenheit, or 1100 degrees Celsius. Because copper and stainless steel have different melting behavior, the copper melts during the process and diffuses into the stainless steel at the connection points. The result is a metallurgical bond linking the internal tubes to the outer plates, and Broad designed the system for mass production. A standard panel roughly 40 feet long and 8 feet wide can emerge from the production line approximately every 2 minutes. But the production speed is only part of the story. The real advantage is what the geometry does structurally. A typical B-core floor slab is approximately 6 inches or 15 centimeters thick, yet it weighs only around 7 pounds per square foot, or about 34 kilograms per square meter. That makes it roughly 10 times lighter than a conventional reinforced concrete slab designed for comparable strength. Then there is corrosion resistance. The stainless steel grade used in B-core is described as being more than 30 times more corrosion resistant than ordinary carbon steel, giving the system an extremely long potential service life. And perhaps most importantly, stainless steel behaves very differently from brittle concrete when exposed to sudden forces. Concrete can crack and fracture. Steel is ductile. Under violent earthquake or typhoon loads, a B-core frame can deform and bend, absorbing kinetic energy rather than simply snapping apart. Broad's claim is that these structures can bend under extreme loading without collapsing, and once you reduce the weight of the building itself, everything else begins changing. Foundations can become smaller, transportation becomes easier, shipping costs fall, and massive concrete columns are no longer required to support an equally massive concrete structure. That is the larger paradigm shift behind B-core. Instead of achieving strength primarily through weight and mass, the structure achieves strength through geometry. Part 7. The Stackable Modular Miracle. The Holon Prefabricated Building System. But a high-strength steel slab is still only a structural component. How do you turn it into an actual building? This is where B-core connects with a construction system that looks almost like full-scale Lego. The Holon Building System. Holon modules are manufactured almost entirely inside a tightly controlled factory environment. Each module is designed around the dimensions of a standard 40-foot shipping container. That choice is extremely important because the global transportation system is already designed around that exact size. Container ships can carry it, trucks can carry it, trains can carry it. So instead of inventing an entirely new logistics network for modular buildings, the modules fit into infrastructure that already exists around the world. And when a module leaves the factory, it is far more than an empty steel box. Its mechanical, electrical, and plumbing systems are already integrated into the floor and ceiling. Triple-pane or four-pane insulated windows are installed. Automatic exterior solar shading can already be built into the structure. Walls contain approximately 22 centimeters of rock wool insulation. Energy recovery ventilation systems are installed to continuously supply filtered fresh air, with the system designed to remove 99.9% of PM 2.5 particles. By the time the module arrives on the construction site, much of the complicated work has already been completed. Then the assembly begins. Because structural beams are already integrated into the floor system, the modules do not require on-site structural welding or conventional wet concrete pouring during the main stacking process. A crane lifts each completed module. Workers guide it into position. The next module is placed above it. Then the modules are connected using high-strength structural bolts, and the speed is extraordinary. In Changsha, Broad demonstrated the system by stacking a complete 11-story apartment building consisting of 56 modules in less than 29 hours. Then, In January 2024, Broad assembled the much larger 26-story Jindu residential tower. Approximately 100 workers operating in alternating shifts, supported by a mobile crane and a tower crane, completed the 26-story assembly in only 5 days. Once the final connections were completed, the building was designed to be essentially ready for occupation. The system is rated to withstand level 9 earthquakes and typhoon-force winds. But there is another feature that fits perfectly with the idea of flexible, resilient infrastructure. The building isn't permanently locked into one location in the same way as a conventional concrete structure. Because the modules are primarily connected with bolts rather than permanently welded together, the building can theoretically be dismantled, transported, and reconstructed somewhere else. If zoning changes, land use changes, or your requirements change, the structure doesn't necessarily have to become demolition waste. It can move. In that sense, Holland takes modular construction far beyond the idea of simply building faster. It turns an entire building into something closer to a plug-and-play structural system. Part 8. The Survivalist's Blueprint. Practical applications for your homestead today. At this point, you may be thinking, this is fascinating, but I'm not planning to build a 26-story skyscraper. I'm trying to build a durable off-grid homestead, a cabin, maybe a workshop. What does any of this actually mean for me? And that question goes directly to the heart of the survival roots philosophy. We don't look at enormous industrial breakthroughs because everyone watching needs a billion-dollar factory. We look at them because the principles behind those breakthroughs can change the way we think about our own self-reliance. Here are 3 practical ideas that bring those principles closer to the scale of an individual builder. 1. Tap into bio-based binders, and bioconcrete traditional Portland cement is heavy and carbon-intensive. But researchers and companies are experimenting with completely different ways of binding mineral materials together. In the United States, Prometheus Materials is commercializing low-carbon concrete mixes that use algae to help produce a natural calcium carbonate binder. In the United Kingdom, BioZeroc is taking another biological route. The company uses specialized bacteria to trigger reactions that bind sand and gravel together. This bioconcrete is described as producing 85% less carbon and can cure at room temperature. For an off-grid builder, the broader principle is worth paying attention to. You don't necessarily have to assume that every stabilized structure must begin with conventional Portland cement. Local clay, lime, and microbial mortar systems all represent different ways of thinking about how locally available materials can be bound together into stable structures. Instead of automatically importing every building ingredient, the first question becomes, what material already exists on the land, and how can it be stabilized? 2. Lego-style polymer sand bricks. Now imagine your local material isn't good angular construction sand. What if you are surrounded by extremely fine, smooth desert sand, or another localized fine aggregate that conventional concrete can't easily use? The German company Polycare approached that problem from a different direction. Its process combines fine desert sand with polyester resin, part of which can come from recycled PET plastic bottles. The resulting polymer concrete can cure in approximately 20 minutes, but the material itself is only half of the idea. The blocks are molded so that they can fit together and be mechanically connected, almost like oversized Lego pieces. That means there is no wet mortar between every course. The system doesn't require the same type of specialized masonry process as conventional construction. And because the blocks are mechanically assembled, they can be taken apart and reused somewhere else. Again, the important idea is modularity. Instead of treating a building as something permanently fused together once and then destroyed when its usefulness ends, the structure becomes something that can potentially be assembled, disassembled, moved, and reused. For a DIY builder focused on flexibility and self-reliance, that principle is extremely powerful. 3. Adopt passive house principles for total energy independence. The Holland system isn't impressive only because it can be assembled quickly. Its energy performance comes largely from something far less dramatic: insulation, and controlled ventilation. Hold-on structures use approximately 22 centimeters of rock wool, or stone wool, insulation. Rock wool is fire-resistant, water-resistant, and resistant to pests. Combine heavy insulation with triple-pane windows, controlled solar shading, and an energy recovery ventilation system, and the energy requirements of a building can fall dramatically. An ERV continuously brings fresh outdoor air into the building, while exhausting stale indoor air. But instead of throwing away all the thermal energy contained in that outgoing air, the system passes both air streams through a heat exchanger. During cold weather, heat from the outgoing indoor air helps warm the incoming fresh air. During hot weather, the process can help reduce the amount of heat entering with the fresh outdoor air. At the same time, filtration can remove 99.9% of dust and allergens from the incoming air. The result is a building that can remain tightly insulated without becoming dependent on uncontrolled air leakage for ventilation. Hold-on buildings are claimed to achieve energy savings of around 90%, and even in extreme cold, approaching -40 degrees Celsius, a highly insulated home, equipped with effective heat recovery ventilation, can maintain comfortable indoor conditions with extremely low heating demand. For anyone pursuing an off-grid lifestyle, that may be one of the most important lessons in this entire story. Energy independence doesn't begin with producing unlimited energy. It begins with needing far less of it. Engineering smarter, building to last. We are living through one of the most remarkable material revolutions in modern history. Limits that once appeared permanent, our dependence on heavy gray concrete, the depletion of natural river sand, and the vulnerability of conventional buildings to earthquakes, are being challenged from several completely different directions. One group of engineers is compressing fresh concrete under pressures as high as 15 MPa and increasing its strength by more than 80%. Another group is using microscopic cyanobacteria to bind loose desert sand into a living protective crust in only months. And another is stacking 26-story modular stainless steel buildings in just 5 days, without relying on conventional wet concrete construction during the assembly process. Different technologies, different materials, different industries. But the message connecting them is remarkably clear. The future of building isn't only about brute force. It's about geometry, biology, and smarter mechanics. It is about getting more performance from less material, turning waste into resources, working with physical forces instead of constantly adding more ingredients, and sometimes working with living systems instead of fighting against them. When you build your own roots, build them to last, build them to survive. So what do you think? Would you live inside a 26-story stainless steel building assembled in only 5 days? Or would you trust a hydraulic press to make ordinary concrete more than 80% stronger? Let me know in the comments below. And if you want to keep exploring new ways to build stronger, live smarter, and become more self-reliant, hit the like button, subscribe, and share this video with another builder. Until next time, stay safe, keep exploring, and keep building your survival roots.